I would say the largest change that has started not too long ago was the use of AI, and it's just beginning to change how we do science and Earth system modeling. So I think I mentioned earlier, we could be using AI to discover different patterns and connections. And now some of our models may be going away. So we're replacing them with AI-based emulators. And I think this change to AI is going to be one of the largest shifts.
Hi, I'm Emma Zareen, your host and a 16-year-old engineering student, policy enthusiast, and hopeful future STEM school survivor. Welcome to She Persists. Before we dive in, I just want to take a second to say how grateful I am for each of you. Every listen and every bit of support genuinely means the world to me. When I started She Persists, it started as a little dream to share real stories of young girls in STEM who are challenging norms, finding their place, and inspiring change. Seeing that idea come to life has been so rewarding, and honestly, it's just the beginning. If you've been enjoying these conversations, I'd love for you to be a part of our community by following this podcast. It's one of the best ways to help us grow, share even more incredible stories, and connect with a wider audience. And I hope the conversation doesn't end here. I hope you carry these stories with you and let them be a constant reminder that your voice truly makes a difference. Today's episode is one that I am very excited about. I'm joined by Dr. Yaga Richter, a scientific leader working to advance Earth system predictability. Dr. Richter leads the Earth system predictability across Timescales initiative as a special projects lead to the director at the National Science Foundation National Center for Atmospheric Research, where she focuses on establishing interdisciplinary collaboration to help us prepare for a more resilient future. What makes her story especially unique is the path that she took to get there. She moved from Poland to the United States at just 13, started college at 14, and earned a degree in mathematics with a minor in physics. In this conversation, we talk about unconventional paths into science, what leadership actually looks like behind the scenes of these large organizations, and why connecting scientific disciplines in other fields is so essential if we want scientific discovery to thrive. So with that, let's get into it. Here is Dr. Yaga Richter. Dr. Richter, I'm so excited to have you here. Welcome to She Persists.
Thank you so much, Emma. And before we start, I just want to say congratulations on creating this podcast. And I think taking this initiative to these kinds of conversations at your age is very impressive. And it really speaks to your curiosity and leadership. So I'm really curious where this all goes. I'm curious to follow you.
Thank you so much. Yeah, this has been really exciting and getting to speak with so many amazing women who've really made their mark on STEM so far and are continuing to as well is just incredible. But before we get into the details of your work, I really just want to ask, how would you describe where you're at in your career right now?
So I would say I'm at a point where I'm less focused on doing science and more focused on helping connect people and ideas and tackle the really big problems. So earlier in my career, success meant publishing papers or developing a model and really being at the core of the science. And I think now it more means asking the questions, are we working on the right problems? What are the grand challenges? What do we need to tackle as a team? Are we organized the right way, etc.? So I would say I'm in a transition place between a senior scientist and an early stage institutional leader. So I have one foot still in science, but another foot in leadership.
Yeah, I think that's so incredible because, as we'll get into later in the episode, you've done so much in the very core scientific field, and the fact that you're able to now share this with others is amazing. So, what's been the main thing that you've been spending your time working on lately?
So most of my time goes to shaping where Earth system predictability research could go next. So asking what questions really matter for the future, how we need to organize ourselves to answer them, what tools do we need. And a lot of these questions are too big for one person to answer or even for one institution. So a lot of my work also tries to go to figure out how to create the right connections, the right structures to make the team science happen. So just before Christmas, actually, I finished a manuscript for the Bulletin of the American Meteorological Society, and it's
Congratulations.
titled, thank you. So it was just accepted on Christmas Eve. It's titled Earth System Predictability Across Timescales for a Resilient Society, a Research Community Perspective. And I wrote that with 24 other people, which is a lot of people to be writing a manuscript with. So a lot of those people came to a workshop we had a year and a half earlier. It was a big workshop where we spent 3 days talking about these grand challenges and what needs to be done in the future and what needs to change in our system. So it was super fun to work with so many people to finally put those thoughts into a coherent small manuscript.
Yeah, and STEM is such a collaborative field, so I totally agree with what you were saying that, these questions are too big for one person to answer. And it's really important that we're able to kind of tie in the strengths of different institutions and different scientists and really find these answers to these big questions. So I think that's amazing.
After I finished that, now I'm working on a commentary piece for a journal that I never work with, but it's called Nature Human Behavior. And it kind of speaks to your point on how we organize science for an interconnected world, because it's largely a human systems challenge. Like, how do we bring all these people together to work on these larger problems?
Yeah, I think that's incredible, especially right now we're working towards, so many big problems like focusing on our environment and how we can have more sustainability. So, I think just really focusing on these big problems that are affecting our day-to-day life as researchers and scientists all coming together to work together, I think that's incredible. So, before we get into the technical details of your work, I want to take a step back and talk about how you actually got here. So, your path into science was pretty unconventional to say the least. You moved from Poland to the US as a teenager and started college at 14 years old. So, what was that period of your life actually like day to day?
Yeah, thanks for asking that. So there was a really unique and challenging time. I moved to the United States when I was 13, and I went for 1 year to high school still. But as many high school students who are smart and into STEM, you learn pretty quickly that that is not always welcome. And the smartest person in the room usually is the person's often the outcast. So I learned, and it's similar things many people learn in elementary school, etc., that being smart and nerdy is not necessarily a way to make friends. So when I went to college at 14, I decided I was not really going to talk about that very much. Actually, I was going to hide the fact that I was 14 because it would automatically make me the odd person out all the time. So I was super lucky on my first day to college. I'm on my train ride because I needed to take a train and a bus to school because I wasn't old enough to drive. So on my first day, I made a friend who was going to go to the same college as I did, and she always did my hair, did my makeup on the train ride. So I looked 18. I was perfect. I probably even looked older. So basically, most people had no idea how old I was. And we kind of kept it that way. So she knew. And then I made another friend who also knew. So they were like my closest friends, but everybody else had no idea. And I liked it that way because then I wasn't the odd person out all the time. But like I said, because I was younger, I couldn't drive. So for 2 years till I turned 16, I had to commute on the bus and a train, which was hard. It took forever. And I also could not legally live in a dorm. So I needed to live with my distant relatives because apparently you have to be 16 to live in a dorm, which makes perfect sense. So there was a lot of little things like that. I had a couple of jobs, so my boss needed to sign paperwork that I could drive late at night because sometimes I worked late. So, there was just a lot of little things like that to overcome.
Yeah, wow. So, how did you even get this opportunity to start college at such a young age?
Well, when I moved from Poland, I went to a school in Scarsdale, New York, called the Ursuline School. And because I was coming from Poland, I did have background in chemistry and physics, and I think our math was pretty advanced. So when they put me into the school, they did put me in a lot of the science classes. So I was taking senior physics, sophomore chemistry, junior computer science, because the intent was I wasn't sure how long I was going to be in the United States, maybe just for a year. So they wanted to make sure I had all the science background because that's where my interests were. And then as a joke, my cousin actually who I lived with started saying, well, since you're taking all these senior classes, why don't you just go to college? What are you going to do for the next 2 years? And it was like this joke she started making over and over until somebody said, well, maybe it's actually not such a bad idea. So, we reached out to a couple of local places, and there was a very young dean at the State University of New York at Purchase. And he had a very, I think, fair idea. He says, well, what's the worst that would happen if I go to college and then fail, right? And they just send me back to high school. So he admitted me and just on the premise that, well, if it doesn't work out, then I can just go back to high school. So I never graduated from high school. I don't have a high school diploma because you can't get the certificate unless you've been a year out of high school. So I couldn't take the EAD or whatever the test is. So yeah, I just went to college without a high school diploma and on this young dean whose name I don't remember, but he was just very open to it.
Wow, that is a very, very unique story and a unique way to end up getting your bachelor's degree. I think that's incredible. But so, can you tell me a little bit more about kind of how college was like for you at such a young age on the more technical aspect and, how you kind of got through these difficult classes and this academic rigor?
Yeah, so the classes were difficult for sure because they were science classes. But I think the hardest part was also because I was coming from Poland and I'm not a citizen here. I needed to raise money for my college. So I needed to keep the grades up, but I also needed to get a couple of jobs. And it was challenging working 20 hours a week during the school week and doing the classes. So sometimes I couldn't give all my attention to the classes. So that was challenging. So there were a lot of, late nights. I was pretty sleep deprived, I would say, substantial amount of time. And for the coursework, it helped to have friends to do the homework with. I was at a college that the classes were fairly small, so that was pretty easy to establish other people you could study with. And the professors were super supportive. So I do remember the professors were super supportive. So if I had any questions or was struggling, I could go ask. There were people to ask.
Yeah, I think what you said about, having that group of people that you can work with holds true for high school now, college, really anything that you're working towards. Just having like a group of people that you can work with just makes, something so much more enjoyable or easier. But wow, that's that's an incredible story. But fast forwarding to now, I want to talk a little bit more about what your work actually looks like today. So, your role currently involves special projects at NCAR. What kinds of situations or needs usually turn into a special project?
Yeah, so my role is fairly unique. I'm the only person who ever had the job that I have. And my main special project is leading the Earth System Predictability Across Timescales initiative. So that does take most of my time. But then in the rest of the time, I do small things such as, giving input to panel comments for the director, to making PowerPoints, to doing larger special projects such as contributing to strategic planning for NCAR, which is like months on end of drafts of looking at strategic plans and mission and vision statements, et cetera, and everything in between. So, really, anything that needs to be done, a lot of the work that I do spans like the needs of the organization. So, connecting people between our different divisions or connecting with the outside, like right now, I'm investigating the storage needs for the community to store seasonal forecasts because one of the databases that's pretty common, it's going away or it's some of the funding is going away, contributing to shaping our AI strategy, etc. So really it's a large scope and there's I would say never a day that's the same.
Yeah, that sounds so. You mentioned that you're the first person who's ever had this title. How did that happen?
That's a also a unique story, but I've been interested in leadership in a long time and the opportunity just came up. Yeah. And I think I just jumped on it.
Yeah, I think that's, the best opportunities come out of impromptu decisions and spontaneous things that come up. I mean, you never really know where they could take you. So, yeah, I think those are always
Exactly.
super important to always just say yes to any opportunity that comes your way.
Yes.
Yeah. So, if a student had would shadow you for a day, what would they actually see you doing?
So they would see me being in a lot of meetings and talking to a lot of people. So from scientists in our organization and software engineers to university professors via Zoom, via Google Meets, sometimes students, also talking to our leadership, talking to like program managers at other institutions, so at NOAA, DOE, etc. And when not in meetings, I would be making a lot of presentations, preparing a lot of talks and also doing a lot of writing. So I think I mentioned the one community paper. Last year I've written a few workshop reports, a couple of opinion pieces. Yeah, a lot of people time and then trying to carve out space to have writing and actually do something done, which is which is difficult sometimes.
Yeah, that sounds like a very busy schedule. And it sounds like you do a lot in your organization. So I think that's amazing. So you came into this field through mathematics for your bachelor's degree. How did that background end up being useful for atmospheric and earth system science?
Yeah, so my bachelor's degree is in math, and at my college, there was a requirement to graduate to actually do a research project. So my physics professor was looking at British Airways data on turbulence. So they actually had the box in the cockpit that they were constantly given data from. And I started applying Fourier analysis to the data to look at when does clear air turbulence happen and try to connect it and figure out whether we can predict it better in the future. So this is how I got interested in the field and was using a lot of the methods that we were learning in our math classes to analyze the data. And then just one day he said to me, well, if you're interested in this, if this is something that's appealing to you, you should go to graduate school in atmospheric sciences. So I had really no idea what that meant, but since I had no other ideas, then that sounded like a good one. And that's what I did. And I worked on like small waves in the atmosphere for my PhD thesis. And a lot of that work I did do with math. So a lot of the just how they are organized and what their properties are, you can derive that using math. So that
Yeah.
was a core part of my PhD thesis thereafter.
Oh, yeah. So that's really cool that you were able to discover this interest early in your bachelor's. And kind of connecting to that, I recently did a project with some people as a part of an internship, and we were also doing something pretty similar with atmospheric sciences. And I definitely saw how big of a portion math was and how much math like really impacted this work. We really got to see like a lot of math formulas and models. It's really cool to see how math can really impact all these big fields that we don't really think about.
Yeah, so like anything in the atmosphere is full of differential equations
Yeah.
and just governed by equations of motion. So it's a lot of physics and a lot of math. And so all the things you learn in like calculus one, two, and three, it all starts coming back to you.
Yeah. I think it's always so cool to see how math can really apply in the real world. A lot of the times when you're in the classroom, it kind of just seems like you're putting numbers on a sheet, but then when you see the bigger picture and it's really, impacting these big scientific questions, it's really interesting to see. So, early on, were you more interested in kind of the numerical side of models or to like the physical processes that they represent?
So early on, I really didn't know what I wanted to do. And actually, I went through the first 8 months of graduate school just taking classes and not settling on the project. And it was only when my advisor gave a seminar, and I still very much remember this because he was pretty getting a little worried about me that I wasn't going to come up with what I was going to do. And then he gave the seminar and he was showing these pictures of these upward propagating waves in the atmosphere. And I said, okay, this is it. This is what I want to do. So then I think it's more of the processes. But then a lot of what my thesis did was modeling of these waves in the atmosphere. And I really did enjoy that. I then did modeling for many years after that.
Yeah, that's so cool that your professor's seminar was able to really help you find that area of passion that you ended up continuing for a long time. That's awesome. So, when did the atmosphere itself become the main thing that you wanted to work on?
So I think it was that day, right? The day of the seminar and picking those atmospheric waves. And I focused most of my time in grad school then learning about those waves and where they come from and then why are they important. And then the other parts of the atmosphere came later. So as I was learning about the gravity waves, then I was learning what they're impacting, and then I would be interested in those other parts of the atmosphere further on.
Yes, getting further into that when you just mentioned the gravity waves. So, your foundation in this atmospheric science region eventually led you to very specific parts of the atmosphere, especially the stratosphere. So, you've worked for years on gravity waves and the quasi biennial oscillation. Can you tell me a little bit more about what this entails and why those processes matter so much for the larger atmospheric behavior?
Yeah, so the small scale waves, which have like horizontal wavelengths of like 10 to 100 kilometers, so they're usually not represented with big models. They need to be what we call parameterized. So you specify equations that represent these motions that are not resolved in the models. And these waves propagate from convection or fronts or mountains, and they go up to the stratosphere. And the reason they're important because they deposit momentum. So sometimes they break, and then there's like an acceleration of the mean wind, and that contributes heavily to what you mentioned, the quasi biennial oscillation, which is an oscillation of the tropical winds in the stratosphere with a period anywhere from 20 to 32 months. So, average period of 28 months. So as those waves break, they can accelerate or decelerate that flow. So they're really important for that. So like I call the QBO like the heartbeat of the stratosphere, right? It's this semi-regular oscillation that's always there, that's always beating. And many people would say, well, why do you care about it? Because it's in the stratosphere, but it has connections to what happens in the troposphere, so where most of our weather is. So the largest connection is in observations to this Madden-Julian oscillation, which is the propagation of convection in the tropics. So the QBO affects that. It affects storm tracks. It affects the northern hemispheric winds in the stratosphere and also below. It's not, so we call this through teleconnections, the importance of the gravity waves.
Yeah, so it sounds like it affects a lot of things that are
Yes.
really prevalent in our day to day life. So, from a modeling perspective, what makes gravity waves especially difficult to represent accurately?
So they're difficult to represent because they vary in scales and also in location. So I focused on the ones coming from convective storms, so like squall lines and mesoscale convective systems, the most vigorous convection, but that is also highly variable, right? So sometimes it's there, sometimes it's very deep, and sometimes it's shallow. So depending on what that convection is, then those waves are different. So you're trying to represent this whole spectrum of waves in a big model, and that is tricky, that is difficult. And also, the observations are pretty slim because these waves are pretty small, but they're pretty abundant in the atmosphere. So we don't have great ways to sensing them all the time. Like we can set up field campaigns and you can do some satellite missions, but it's been tricky to characterize them correctly from observation. So that's something we're still working on.
I see. Well, you're doing very groundbreaking work to making this easier to model and to recognize. So, but all of that ties into a bigger question that you've spent a lot of time on, predictability across different timescales. So, you've worked extensively on subseasonal to seasonal prediction. What makes that timescale especially challenging compared to short-term weather forecasts or long-term projection?
Thanks for that question. That's a great question. So the subseasonal prediction is challenging. Uh, they call it the predictability desert. And the reason they call it that is because it's a time window where predictability from like the initial state starts wearing off. So the weather forecasting is largely based. We can do this because we know the initial state of the atmosphere and the ocean, and then we can solve the equations and know what's happening after. And then like seasonal and longer climate predictions often come from like the memory in the system. So from these larger modes of variability, for example, like El Nino Southern Oscillation, or there's maybe snowpack anomalies, soil moisture anomalies. But in this window, subseasonal window of like week 3, 4, and even up to 2 months, you're neither in this region where boundary forcing helps you or where initial conditions help you very much. So it's trying to figure out where are the sources of predictability and why sometimes we can get a really good week 3, 4 forecast and why often we cannot. So the week 3, 4 forecasts are only skillful some of the time, maybe about 30 to 40% of the time. So the question is really to figure out how accurately can we predict when they're going to be skillful.
Oh, that's interesting. I didn't know that it was difficult to predict at that time period and that the accuracy level was only 30 to 40%. That's interesting. That really does open the door to a lot of big questions about, how you can improve this accuracy and what limits this accuracy and such. But yeah, that's awesome. So, in models like the Community Earth System model or the WACCM, the whole atmosphere version of NCAR's Earth system model, what tends to limit predictability the most at those immediate timescales?
So that's a great question, and we probably don't have one single answer because there's many factors. So I'll mention a few of them. So one of them is resolution. So those models mentioned CSM and Wacom, they usually run with resolution of about 1 degree, so about 100 kilometers. So that means those grid boxes on which the equations are calculated, they're 100 by 100 kilometers in the horizontal, and they're much smaller in the vertical. But 100 kilometers is still a pretty big area, 100 by 100, right? So there's a lot of errors introduced from not knowing what exactly things look like inside of small boxes. So a lot of those processes are parameterized. So that contributes to errors. I would say that's one of the largest. It would be like the physics parameterization, the resolution. Also, the initial state of the atmosphere, the most and the other components. So the better your initial state knowledge is, the better the forecast. And we know this pretty well for the lower atmosphere. We have really good observations, but we're still lacking like global ocean observations and good observations of land. And again, at those intermediate time scales, the predictions are not only dependent on what the atmosphere is doing, but what other components of the system are doing. So, like what the ocean and land are doing. So I would say better observations and knowing how to assimilate them, resolution, representing processes. Yeah, so quite a bit of things.
So, for the resolution that you mentioned, it's 1 degree. What is kind of like the key thing that's limiting scientists from being able to narrow down that area from 100 kilometers by 100?
So that's computing power. So we have models, global models now that can go down to about 3 kilometers, but they're very expensive, right? So the if you go down to that resolution, it's 100 times more expensive or even more to run that model. So then you need more computing time, and the computer speeds have not caught up to the needs of what we want. So that is one of the frontiers in Earth system modeling is these high global 3 kilometer simulations. But even at 3 kilometers, if you think about it, convection, sometimes those storms and those updrafts are scales of like 1 kilometer. So you still are needing to prescribe what happens inside of those 3 kilometer boxes. But yeah, computing power is limiting. But that's where AI is really coming in. So perhaps with AI, we can use AI to represent some of the processes in the model to make them more efficient. So if you can replace some of the expensive physics with a simple AI parametrization, they could get you closer to running a global model at a finer resolution.
Oh, that's really interesting. Yeah, definitely. I've heard that computing power for a lot of different types of model gets more expensive the more accurate you're trying to get. So that totally makes sense. But how do modelers decide when adding more complexity can actually improve the skill versus when the model just becomes harder to interpret?
So that's one of the greatest research questions, right? Is what complexity of a model do you need for what problem? And it's tricky because often like we develop an Earth system model for many applications. So like our community Earth system model, we develop for looking at the subseasonal timescales, also looking at decades ahead. And you need different complexity of processes for those different phenomena, but perhaps you only get one model to develop. So this is some of the things we're thinking for the future is to make these models more have more interchangeable components, to make it easy to switch components on and off, to really do that research like what do you need for subseasonal prediction? So one of the research projects I worked on was to see how much the stratosphere matters for subseasonal prediction. Because if you want to include the stratosphere, then you need to pay for the cost of having all those levels, right? And then actually, we found that it most of the time it wasn't all that helpful for subseasonal prediction. Sometimes, but if you were running an operational forecast, you may want to make the choice that you run more ensemble members of a cheaper model and get a little bit more skill from that rather than adding complex physics. So that's where the research is really important is to figure out what is that you really need for your specific problem.
Yeah, I think that's always super important to just be able to, set the parameters of what you're looking for and what's actually necessary versus what overcomplicates the problem a little bit more. But as your work has grown more interdisciplinary, your role itself has changed quite a bit. So, what part of moving into more senior or leadership roles took the longest to get used to?
I've really enjoyed transitioning to leadership. So I think there wasn't anything particular difficult about the transition. But what I've noticed is what you need to develop is the ability to constantly pivot between different topics. So it's really not uncommon in my day to have 6 plus or more meetings, and each one is about something completely different. So I may start my morning with space weather, and then the next one may be talking with United Nations about their needs for prediction. And then my next meeting may be about something completely different, like related to a personnel issue on a team. And the next one may be on strategic planning, right? So it's just the ability to go from one topic to the next that are really often not connected to each other.
Yeah, I think that's always a big thing in leadership roles is being able to juggle everything and being able
Yes,
to, put your foot in like every single boat that there is. So, yeah, I think that's definitely a big
exactly.
thing that
Yes.
changes from going from, like one category or one subfield to just being open to everything. But yeah, so what does your work involve now that it didn't earlier in your career when you were more focused on just the core science?
So I think I have a lot more contact with people in leadership positions. And also, I talk to a lot more committees and boards and give a lot more presentations. So obviously, inside our organization, I spend a lot of time with the NCAR director and our other leaders, but also on the outside. So like talking to program managers at NSF, at DOE, NOAA, organizing workshops, being part of other committees. So just a broader network of people that I work with.
So, to wrap things up, I want to reflect a little bit back onto your field and your career as a whole. So, having worked in the field for nearly 2 decades now, what's something about Earth system science or Earth system modeling that has changed significantly since you first started?
So I think what has changed significantly is the computing power and the resolution of the models that we're going towards. But I would say the largest change that has started not too long ago was the use of AI. And it's just beginning to change how we do science and Earth system modeling. So I think I mentioned earlier, you could be now replacing parts of the model with AI. We could be using AI to discover different patterns and connections. And now some of our models may be going away, right? So we're replacing them with AI based emulators. And I think this change to AI is going to be one of the largest shifts. So, which is, we're just starting to observe that.
Yeah, I think that's such a big thing now, and I could go on like a whole tangent about this, but the way that AI is really changing the way we even approach research and the way we approach science. And, AI didn't really even start taking off until pretty recently, not too long ago, but just seeing how fast that's impacting the scientific research field and just how much is changing in terms of, like you said, modeling, computing, and how it's impacting scientists and researchers and really causing them to change their approach on a lot of things, but it's also so beneficial. And like you said, you can shift your focus from some models that AI can really focus on and shift that focus to more higher computing powers and just being able to focus on other things. So I think that's, a huge thing that you mentioned that's really changing in all scientific fields.
Yeah, and I imagine it's also shifting for the younger people how they do their work. So, like, I actually had to find all the bugs in my code, right? You can just take a piece of code, put it in AI bot, and it's going to tell you exactly where you've gone wrong in 3 seconds,
Yeah.
right? So, I think it can even write the code to analyze your data for you. And I think that's such a difference where your time is going to be going in as scientists, early career scientists, because you don't have to do all of that we used to have to do ourselves.
Yeah, and I think in the past couple years, AI has just taken off a lot, and I can't even imagine by the time, I'm graduating college in like 6 years where that's gonna go and how much that's gonna impact and how much is gonna change. So I think that's a really big thing to think about, and especially when approaching like what kind of research you want to focus on and where you want your niche to be. I think, yeah, that's definitely gonna change a lot of things and change a lot of factors of research. So, what do early career scientists often misunderstand about how this field actually works day to day?
So I would say a lot of early careers underestimate how much science depends on people relationships because a lot of day to day is around making plots and analysis and finding data and a lot of that. But I think the communication is a big piece and getting your ideas in front of the right people, and especially just finding ways to be heard and seen when you're starting out. So having a good mentor tremendously helps with this. But, science is just a very big field. There's so many scientists out there. So to really get your idea across the communication is a key piece. And I think especially I've been over the years surprised how much resistance there can be to new ideas. So even though scientists are supposed to be open and they are to new ideas, they scrutinize all the ideas. So there's always a little bit of a resistance, right? So if you're trying to change how something is done, an established way of thinking, it is a little bit of an uphill battle. So that persistence is really important.
Yeah. I think what you said about having a good mentor, that's so incredibly important, someone who can really guide you through the struggles and like you said, persistence and having a mentor can help you so much with that and just, having someone who can open your eyes to so many big things in the scientific world is definitely so important. So, what's one piece of advice you would give to high school or undergraduate students looking to pursue a similar field?
So I would say get involved in research as early as you can, and use the time to figure out what you're actually passionate about. So find an advisor that resonates with you. And if you're not enjoying the project or the team, don't assume that science isn't for you. It's just maybe that team or that advisor is not the right fit, because the experiences of early careers and students, I think, vary tremendously. Even you can come to the same organization and I have two students and they'll have a completely different experience based on the people they work with and how good that alignment is and fit. And sometimes it's not a problem with the advisor. It's just not a good fit or the interests are different. So yeah, encouraging and looking for those people who are open to new ideas. Who if you mention something that's completely out of the box, they're not going to laugh at you and tell you, "Oh no, that's a silly idea," right? So you really want to find the people who are open-minded.
Yeah, and I think to kind of add on to what you just said about, having completely different experiences based on who your mentors or advisors or group is. I think it's so important to remember to never feel stuck in an environment. You can always shift from one research question to another if you just feel like this is not the space for me or like this is not something that interests me. So I think that's a really big thing. Sometimes people feel like science isn't for them because they had one experience where that wasn't a well-suited field for them in that specific research field. But I think there's something in science for everyone and never feel stuck in the place you are, the team you're on, and yeah. So if you could give yourself one piece of advice as a high schooler when you were younger, what would it be?
So I would say, yeah, go after the people that you find inspiring. So if you want to work with someone, even if you think they're very senior or they may not want to work with you, just go and try it because often those people are primarily looking for match in passion, match in interests, and the go-getters, right? It's interesting when you're on the other side and picking who you want working with you. It's often the passion and the drive that will trump your knowledge in programming or skills because that is in the end the drive and the passion is what's going to get you through the hard problems. I would also say invest in learning to communicate your work and advocate for yourself because if you're lucky you'll get a great advisor who will do that for you, but even so those are great skills to have. And then maybe thirdly, like invest in the relationships with your colleagues and mentors because as you go on, your colleagues in college or in graduate school, they're going to be then your peers later on in
Yeah.
life as well.
Yeah, networking is such a big thing in the science field. You never know where you're going to meet someone or where opportunities will come from. And just keeping good connections with people and reaching out to them and just working together to kind of improve as a big scientific community is so important. Well, Dr. Richter, thank you so much for taking the time to share your story. It was really interesting to hear about your path into Earth system science, what your role at NCAR actually looks like, and how your experiences have shaped the way that you approach both science and now your leadership roles. So, to everyone listening, thank you for tuning in to this episode of the She Persists podcast. If you enjoyed this conversation, be sure to follow along and share it with someone who might find it interesting as well. And until next time, thank you so much for listening.
Thanks so much for having me.
Once again, I'm your host, Emma Zareen, and thank you so much for tuning in to today's episode of the She Persists podcast.